This video is on stoichiometry of gases that are at STP. This first thing is called Gay-Lussac's law of combining volumes. So if we have a reaction that is all gases, okay, so we have nitrogen gas here, hydrogen gas, producing ammonia gas. If we have 12 liters, saying there's 12 liters of that, well, we can just look at the ratio here. So usually we say this is a mole ratio. Remember, if we're at STP, or if we're at the same temperature and pressure, 2 moles of that gas, if we were at STP, would be 44.8 liters. 3 moles of that gas would be 22.4 times 3. A mole of that gas would be 22.4 liters. So if we were at STP, those would all be in a 1 to 3 to 2 liter ratio. Okay, so we can use those as liter ratios. Now, if this one was like at STP, and these gases were being mixed at something not standard, now we can't use these as liter ratios because they would not be the same anymore. But most times a reaction occurs here, and the products are typically collected at the same temperature and pressure. Or if they're not, then we'll let you know that. But if they're at the same, then we can just go, well, you have 12 liters of NH3. That means for every 2 liters of NH3, there's 3 liters of hydrogen. So that means 18 liters of hydrogen there. Now, if they were at different temperatures and pressures, I would have to convert this into moles at that temperature and pressure, do my mole ratio back to that, and then use P equals nRT again to get my volume of this at the different temperature and pressure. So I'd have to do P equals nRT twice in that situation. All this stuff today is going to be at STP, so these are all at STP. So remember, that means when things are at STP, we can use 1 mole equals 22.4 liters. Okay, so we don't have to use P equals nRT at any point in time in these questions. So this one's asking for grams needed to produce 9.5 liters of NO, so 9.5 liters nitrogen monoxide. Again, just like normal stoichiometry, if we're in liters here, we want to go 22.4 liters is a mole. Sometimes people get confused. Remember, these are gases, so we can use that. Okay, it's not solution stoichiometry anymore. We're using molarity. It's just a molar conversion with gases. We're liters of that, so once we do that, we get our mole ratio 4 to 4. For every 4 moles of NO, there's 4 moles of NH3. We want to get into grams. Every 1 mole is 17 grams. Answer there is about 7.2 grams of ammonia. So normal stoichiometry, we just now can use this ratio right here. How many liters of NO are formed from 7.5 liters of O2? Okay. Again, we can do a liter-to-liter ratio here. If you don't do that, that's fine. So if you did it without it, you'd do 7.5 liters of O2. Converting that to moles, I'd say 22.4 liters is a mole of O2. My ratio, O2 to NO, sorry, I'm doing a video. Does it?
Sorry.
That's all right. Mole 2, so we're going to go 5 moles of O2 to every 4 moles of NO. So we'd be at moles of that, and then we'd say every mole of NO is 22.4 liters. Now notice, we divided by 22.4, and we multiplied by it. So all we really did was our ratio. So this ratio can be in liters if they're both gases. If they're gases and they're at the same temperature and pressure. Now, if they weren't gases, we can't do that. Liquids and solids have way different volumes than gases. Answer there then is 6 liters. 6 liters NO. Last one down here, you have 0.36 moles of oxygen. So we're going oxygen to NO again. So 0.36 moles of O2. Again, if you start with moles, you're going right to your ratio. For every 5, there's 4. For every 5 moles of O2, there's 4 moles of NO. Then it's asking for liters. Again, it could ask for grams, could ask for moles. We'd stop right there, but it's asking for liters. So then, since we're at STP, every mole is 22.4 liters. Sorry, you probably can't see that very well. Touch it down down just a little bit. Answer there is 6.45 liters. So those should be fairly simple stoichiometry. We'll do ones not at STP in a different video.